Hi, hello. For this video, we're going to discuss about our third part of amplitude modulation, which will focus on AM transmitter, particularly the amplitude modulation modulating circuits. Okay, so from the past um, discussions regarding amplitude modulation, so we have discussed the theories and, of course, some computations that are important for amplitude modulation. So for this video, we will be discussing about AM transmitters. Okay, so to start with, we can see here the simplified block diagram of an AM transmitter. Okay, so what happens in our AM transmitter? So we have here in modulator, the audio modulates the RF amplitude. Okay, so there are two devices to generate AM. So we have here your transmitter. Okay, so if you're going to generate or if you're going to transmit high powers for high efficiency or complex waveforms, we are going to make use of AM transmitter. However, we also have what we call AM generators, and AM generators are usually for laboratory purposes. Okay, so what do we mean by laboratory purposes? So when we have low power level or simplicity is a must, then efficiency. So we just wanted to generate your AM signal, so we can make use of AM generator. Okay, so we have here the basic block diagram. So in modulator, the audio modulates the RF amplitude. So we have here your RF oscillator, okay, or in the before going to the modulator, so we have technically two inputs. So usually our intelligence signal or our modulating signal is your microphone, okay, and then your RF oscillator, wherein this will generate your RF oscillator will generate your carrier signal and then passing through your modulator. So this video, we will be discussing what type of circuits can act as your modulator. And then after that, you have your power amplifier, okay, so for strengthening your signal, and then you have your low pass filter to filter out unwanted signal. And of course, it will go through your antenna for transmitting that to an appropriate medium. Okay, so your medium can either be the free space or it can be through your cables, etc. Okay. Okay, so what does the transmitter do? Okay, so or what does the modulator do? So the modulator converts the frequency of the input signal from the audio range. So your audio range in this figure is from 0 to 5 kilohertz. Okay, so this is our modulating signal. This is our intelligence signal that we wanted to transmit. However, this frequency is too low for long distance transmission. So what do we do? The one purpose of your modulator is to convert this frequency to the carrier frequency of a certain station. So for example, our station is 610 kilohertz. Okay, so this is the carrier frequency of the station is ranging from 605 to 615 kilohertz with a 10 kilohertz bandwidth. So that bandwidth is the allotted bandwidth for AM transmission. Okay, so it's from 605 to 615 with the center carrier frequency equivalent to 610 kilohertz. So this is the frequency domain representation of your input, and this is the frequency domain which is the representation of our output. So from your low frequency range, your modulator converted it to a higher frequency, which is the frequency of your which is included, or the frequency of your carrier signal. Okay, so we have here the receiver block diagram on the other end. Okay, so from the antenna, so we also have what we call the receiving antenna. So the antenna that we have seen a while ago is your transmitter antenna. So this time we have your receiver antenna. So what it can receive is the signal with a very, very high frequency. So that is your RF amplifier. So from the space, it is uh considered attenuated. So what do we mean by attenuated? So the signal strength becomes very, very low due to some noises that was able um, to be included in your signal once it is being transmitted through free space. So we need to amplify it first. So we have here for your first stage is your RF amplifier, because basically what the antenna here will be receiving is uh, a radio frequency signal or a high frequency signal. And then we have IF mixer. So we cannot directly down convert your radio frequency to your audio frequency signal. So we have this intermediate frequency. So IF here stands for intermediate frequency. So we're going to this time make your frequency lower. Okay, so at the transmitter side, we increase your frequency. So this time we're going to decrease your frequency. Okay, so we're going to make it lower, and then we're going to amplify that specific intermediate frequency. And then we have here your envelope detector. Actually, this envelope detector here is our demodulator. So we will be discussing demodulator on our next video. Okay, and afterwards, since it was already the signal was already demodulated, that means from the intermediate frequency we have already recovered. Okay, so we have already recovered your original signal in the audio frequency range, so that audio signal will now be amplified. So using your audio amplifier, so there will be different amplifiers depending on the frequencies that we are amplifying. Okay, so you have your RF amplifier for higher frequencies, you have your IF amplifier for your intermediate frequencies, and then you have your audio amplifier for your original signal frequency. Okay, and then of course the output for our receiver is your speaker or your radio. Okay, so in amplitude modulation, we have two types. Okay, so we have two types. We have basically the low level modulation, and we have the high level modulation. So what is the main difference or similarity between the two? Okay, so the location in a transmitter where modulation occurs determine the type of transmitter. So it is not necessarily, it doesn't necessarily means that low level modulation is a lower type of modulation process, or a high level modulation is the more what do you call this, we wanted high modulation. So it has nothing to do with that. Okay, so the term low level or high level modulation, um, the thing that will differentiate the two is the location in a transmitter where actually modulation takes place. Okay, so we have here what we call low level modulation. Okay, so this takes place prior or before the output element of the final stage of the amplifier. So prior, it is depending on what type of final element or output element that you are using. So this is prior or before. Okay, so when we are using transistorized transmitter, so we are talking about this is prior to the collector. Okay, because the collector is the output terminal of your transistorized transmitter. However, if you're going to make use of FET transistors, then we are talking about the drain, because the drain is the final stage of your FET transistor. Or in older types of transistors wherein we are still using vacuum tubes, then we are referring to the plate. Okay, so plate is the final stage when you are using vacuum tubes. Okay, so in low level modulation, so low level modulation doesn't actually low-level modulation actually is defined as the modulation that takes place prior to the output element of the final stage. Okay, so in low-level modulation, we need less modulating signal. Okay, so less modulating signal power is required to achieve a high percentage modulation. So if you're still going to remember, so our highest percentage modulation is 100%. Okay, so in low level modulation, it requires less modulating signal power to achieve a high percentage modulation, and this is one advantage of your low level modulation. Okay, however, when we are talking about high power applications, all the amplifiers that follow the modulator stage must be linear amplifiers. So in this case, this is somewhat a disadvantage of low level, because since your requirement is less signal power, so therefore if we are going to make use of low level modulation in high power applications, all the we will be needing several amplifiers, okay, to follow the modulator stage, okay, and those must be designed linearly. Okay, so this is extremely inefficient. Okay, so this is extremely inefficient if we're going to talk about low level modulation. So why inefficient? Because it requires a much higher amplitude modulating signal to achieve a reasonable percentage modulation for this. Okay, so um, usually, the final modulating signal amplifier must supply all the sideband power, and that sideband power is usually 33% of the total transmit power. Okay, so this high power up, it is very very inefficient when we are talking about high power application. So therefore we just limit low level modulation to much lower application. Okay, so we have here high level modulation. So what is the difference between low level and high level? So for high level modulation, the modulation takes place in the final element of the final stage where the carrier is at its maximum amplitude. So that is just their main difference. Okay, so low level modulation takes place prior, while high level modulation takes place in the final element. Okay, so that is their main difference. Okay, so we have here an example of a low level modulator. Okay, so we have here your this is a small signal. So as you can see, if you're going to look at the figure, so this is just like the usual voltage divider configuration um, that we are discussing, okay, in our electronic subjects. However, we just need to place another signal here. So this signal here is for your modulating signal. Actually, the difference is that, so this is just the same voltage divider configuration. The only difference is that it has two inputs. Okay, so for modulators, of course, you will be needing two inputs. Okay, so we have here your low level modulator. This is a small signal class A amplifier. Okay, so it definitely has two inputs. So our first input is your carrier here, which is directly connected across your base terminal. And then we have here your modulating signal, which is being applied across your emitter junction, okay, or emitter terminal. So since the modulating signal is applied across your emitter terminal, we call this class as emitter modulation. Okay, so why emitter modulation? Because your modulating signal is applied across your emitter junction. Okay, so this has two inputs, your carrier at the base and your modulating signal at your emitter. Okay, so without modulating signal, okay, without this one, Your transistor, your circuit is just operating as a linear class A amplifier. Okay, so when we have here your input, we have here your output. And your output carrier, okay, so the output here is your carrier signal which is amplified by your quiescent voltage gain. Okay, so of course, this is a voltage divider. We can solve for the gain. So you know how to solve for the gain of this. So we call that your quiescent gain. So without the modulating signal, we are just operating just like a linear class A amplifier. So the output here is just your output carrier amplified by the quiescent voltage gain. So what happens when we have here your modulating signal? So when we apply your modulating signal here, it starts to have a nonlinear operation. Okay, so what nonlinear operation is occurring? So we are now having a signal multiplication. Okay, and your nonlinear operation or signal multiplication is your definition for modulation. Okay, so it is now acting as a modulator circuit. So your carrier is being applied to the base, okay, and it is being modulated upon by your modulating signal that is being applied across your emitter region. Okay, so the operation. Okay, so the modulating signal varies the gain of the amplifier at a sinusoidal rate which is equal to the frequency of your modulating signal. Okay, so the depth of modulation achieved is proportional to the amplitude of your modulating signal. So this is the mathematical expression for our voltage gain. Okay, so our voltage gain is given by AQ, wherein AQ is the amplifier quiescent voltage gain. So we can solve for the amplifier quiescent voltage gain without either your carrier signal and your modulating signal. Okay, and then you have, so AV is the amplifier voltage gain with modulation. So how did we know that modulation already takes place? Okay, so because of the appearance of your M here. Okay, so when we have your modulation index, that means we have already modulation. Okay, so modulation already occurred. And then, of course, you have sine of 2 pi fmt, wherein your fm is the modulating frequency of your um, modulating signal. Okay, so your sine 2 pi fmt goes to maximum to minimum. Okay, so 2 pi fmt, so the maximum value can be positive 1 and the negative and the minimum value could be equivalent to negative 1. So plus or minus 1. Okay, so therefore imagine if this is equal to 1, if your m is equal to um, if your m is equal to, if your sine 2 pi fmt is maximum, therefore it will be equivalent to 1. So it will be, your equation will be equivalent to aq 1 plus or minus 1. So therefore, the maximum available output voltage is equivalent to twice your amplifier quiescent gain. Okay, so twice. So, but if this is equivalent to negative 1, so this will be equal to 0. So, your AV minimum is equivalent to 0. So, your voltage gain is ranging from 0 to 2 times your amplifier voltage gain. Okay, so your modulating signal can either be your modulation percent coefficient can either be 100% or 0%. So that is your maximum and your minimum value. Okay, so these are the output waveforms. So these are the output waveforms for our emitter modulation. Okay, so the amplitude of the output signal depends on the amplitude of the carrier and the voltage gain of your amplifier. Okay, so the coefficient of modulation depends entirely on the amplitude of your modulating signal. Okay, so the modulating signal again is being applied through isolation transformer T1 to the emitter of our Q1. Okay, so and then your carrier is applied directly to the base. So your modulating signal drives your circuit into both saturation or cutoff. Okay, so since without modulating signal, this is just linear operation. So therefore, you are just operating at the active region of your transistor, depending on the gain of your uh, uh, amplifier here. But with modulating signal, this now drives your circuit into both saturation and cutoff. So when your circuit is driven to both saturation and cutoff, that is what we mean by nonlinear operation. Okay, so upon driving them both to saturation and cutoff, we are producing the nonlinear amplification which is necessary for modulation to occur. Okay, so the collector waveform includes, so where is your collector waveform? So your collector waveform includes the carrier and the upper and the lower sideband. Okay, so this includes carrier and the upper and the lower side frequencies rather. Okay, so we have your C2. Where is your C2? So this is your C2. This is your coupling capacitor. Okay, so what does your coupling capacitor do? So this removes the modulating signal frequency from the AM waveform. Okay, thus producing a symmetrical AM envelope at V out. Okay, so this serves as your what do you call this, coupling capacitor, and it cuts away your modulating frequency at the output. So at the output, what we can see are just three frequencies. So what are the three frequencies available here? Just the carrier frequency, the upper sideband frequency, and the lower sideband frequency. So remember, we cannot totally see your modulating signal at the output side, just the sidebands and the carrier. So how do we remove the modulating signal? So it is the function of your C2 here. Okay, so the analysis is very simple for this type of circuit, okay, for this low level modulator. However, since this operates in class A, so what do we know about class A amplifiers? So since this operates in class A, it is said to be inefficient. Okay, so we know that class A amplifiers have a very low um power efficiencies. Okay, and likewise, it is incapable of producing high power output waveform. So why is it incapable of producing high power output waveforms? Because in class A amplifier, we are just limited on the very small part of your active region. So technically, we are just using this for low power applications. Okay, so this is the circuit is very simple. However, it is has a disadvantage of in being inefficient and incapable of producing high power output waveform because it is operating on class A. Okay, so we have here an example. So it says here, for a low-level AM modulator, similar to the one shown, okay, so the one that we have in our previous slide, okay, so with a modulation coefficient equivalent to zero point 0.8 and a quiescent voltage gain equivalent to 100, an input carrier frequency FC 500 kilohertz with an amplitude equivalent to 5 millivolts, okay, and 1000 hertz modulating signal. So we are to determine the following. Okay, so we are to determine the maximum and the minimum voltage gains, the maximum and the minimum amplitudes for V out, and we're going to sketch the output envelope. Okay, so I have here the solution, okay, for this problem. So to solve for the maximum, Okay, so to solve for the maximum and the minimum voltage gain, we have to determine the voltage gain wherein modulating signal was already applied. Okay, so the given gain there is your quiescent gain. So that means it is considered as without the modulating signal yet. Okay, so how do we know the minimum and the maximum voltage gain? So the minimum and the maximum voltage gain is given by AQ, which is your quiescent voltage gain. You have 1 plus or minus M. Okay, so we have here the plus M for the maximum value and the minus M for the negative value. So giving us your AV max equivalent to 100 plus 1.8, 1 plus zero point 0.8, so that will give you 180, and your AV minimum equivalent to 100 multiplied by 1 minus zero point 0.8. So 1 minus zero point 0.8 is equivalent to zero point 0.2 times 100, so that will give you 20. So with the applied modulating signal, our voltage gain is from 20, which is the minimum value, and 180, which is the maximum value. Okay, so therefore, determining now your output voltage, so that is simply the gain multiplied by the input voltage. Okay, so if we have an input voltage of 5 millivolts, your maximum V out is simply 180, which is your maximum voltage gain times your 5 millivolts, and that will give us zero point 0.9 volts. Okay, and our minimum output voltage is 5 millivolts multiplied by your minimum voltage gain, which is 20. So that will give us zero point 0.1. So the output and minimum output now, the maximum and the minimum output now is ranging from zero point 0.1 to 0.9. So how do we draw the AM envelope? Okay, so the AM envelope, so the maximum amplitude specifies your zero point 0.9 here, while the minimum output voltage specifies your minimum voltage here, okay, or your V minimum. So that will be your V max and your V min. Okay, so in this case, this is our figure. Okay, so this is our figure for your output waveform. So this is your zero point 0.9, which is at maximum modulating signal, and zero point 0.1 for minimum modulating signal. Okay, so the problems for this type of circuit is very simple. Okay, it's just like this one. Okay, so next is we have a simplified still medium power transistor AM double sideband full carrier modulator. Okay, so we have here a simplified medium power transistor AM double sideband full carrier modulator. So before 1970s, before solid states or before transistor was discovered, medium and high power AM transistors or transmitters uses vacuum tubes. Okay? So, but in mid-70s, solid-state transmitters have been available with output powers as high as several thousand watts. Okay, so several final power amplifiers in parallel are connected such that their output signals combines in phase, thus they are additive. Okay, so this type of medium power transistor modulator is called collector modulator. So why collector modulator? Because as you can see, the modulating signal, okay, so this is our modulating signal. It is being applied at the collector terminal of our transmitter. So earlier in our first example, it is called emitter modulator because the modulating signal is applied at the emitter terminal. So this time we call this collector modulator because as you can see, the modulating signal is applied across your collector terminal. So your unmodulated carrier, just like the previous example, is still being applied across your base terminal here. Okay, so the collector is the output element. Okay, therefore it is the final active stage of your transmitter. So what do we mean by it is the final active stage of the transmitter? So there is no amplifiers between it and the antenna. So actually after modulation, it will be right away being transmitted. So this is the definition, this is our definition for a high level modulator. Unlike for low level, so the modulation takes place before the output. So therefore your output is your amplifier stage. So therefore whatever the product of your modulation, it will still be amplified. So in this case, since modulation takes place at the output element or the final active stage of your transmitter, there are no amplifiers between it and the antenna. Okay, so we call this as high level modulator. So this is our definition for high level modulation because amplifier takes place at the collector. Okay, so technically to achieve high power efficiency or of 80% or higher, so it makes use of a class C operation. So unlike our previous example, it is class A. So we use class C here. Therefore, we have a higher power efficiency. Okay, so we can achieve 80% or higher. So again, just like the previous one, we still have two inputs. So your two inputs are your carrier input at the base and your modulating signal at the collector. Okay, so this is biased as class C. This operates nonlinear and it is capable of nonlinear mixing. So nonlinear mixing, this is our modulator process or modulation process. Okay, so the modulating signal is applied directly to the collector. So we have here a new parameter, which is your RFC. So your RFC stands for radio frequency choke. So what is the function of your radio frequency choke? So this isolates the DC. Okay, so what is our DC component here? So our DC component here is your VCC. So it isolates your DC power supply from the high frequency carrier and the side frequencies while still allowing the low frequency intelligence signal to modulate the collector Q1. Okay, so technically it is isolating your three different frequencies, okay, and still allowing your intelligence signals to modulate your your um collector the collector part of your Q1. Okay, so how does this operates? So we have here the operation of your collector modulator. Okay, so when the amplitude of the carrier, okay, so we have here your carrier signal. When the amplitude of your carrier exceeds zero point 0.7, so what is the significance of zero point 0.7? So this is the barrier potential of your base emitter junction for a silicon transistor. Okay, so when the amplitude of the carrier exceeds zero point 0.7, your Q1, okay, so your Q1 here turns on. So when it turns on, your IC, okay, so your IC, your Q1 here, your collector current or your IC starts to flows. Okay? Start to flow. However, when your input here, when your carrier here drops below zero point 0.7, your Q1, Okay, so your IC stops flowing. So therefore, your Q1 switches between saturation and cutoff, which is controlled by the carrier signal. Okay, so when it exceeds zero point 0.7, it turns on, so therefore IC flows, and when it is below zero point 0.7, your Q1 is off, therefore IC stops flowing. So your Q1 is switching, okay? So it is functioning as a switch wherein it switches between saturation and cutoff, which is being controlled by your carrier signal. Okay, so for Class C operation to be achieved, your IC must flow for less than 180 degrees of the input's cycle. Okay, so that is our definition for Class C operation. So your Q1 turns on just for an instant. Okay, so very fast because it is just for less than 180 degrees. So your Q1 turns on for an instant, allowing current to pass for a short time only. Okay, so the output is a negative going, so this is your IC, very short pulses. Okay, this is your IC, very short pulses when your input is above zero point 0.7. Okay, so our output is a negative going waveform at the collector. Okay, take note, this is a common emitter configuration. Therefore, your output is what 180 degrees out of phase of your input. So if we have here a positive pulse or a positive going pulse, our output is negative going pulse. Okay, so during the time that we have no conduction, our output is equivalent to 0. And then we have again your output waveform here. Okay, so as you can see from the figure, your output voltage looks like a repetitive half wave. Okay, so this looks like a half wave rectified signal with frequency, of course, equivalent to the frequency of your carrier signal. Okay, so when your modulating signal is applied to the collector, which is in series with your DC supply, it adds, okay? So it either adds up or it either subtracts from your VCC. Okay, so from our figure here, we can see that the maximum peak modulating signal, okay, so the maximum peak modulating signal is equivalent to VCC. So peak voltage is equivalent to VCC. So therefore, you are we are having an output which is equivalent to, okay, the maximum which is equivalent to 2 VCC, and the negative and the minimum which is equivalent to 0, or your VCE saturation. Okay, so when we have peak change in your carrier voltage or carrier voltage amplitude, that is equivalent to the peak change is equivalent to VCC. Okay? So your output signal here also resembles a half-wave carrier superimposed onto a low frequency AC intelligence signal. Okay, so in this case, your Q1 here, transistor Q1 here is operating nonlinear. So the collector waveform contains two frequencies. So what are those two frequencies? Your FM and your FC. But not actually FM, but rather you have your carrier frequency plus and minus your modulating frequency. Okay? And this must be band limited before transmission so that we don't have any other frequencies other than your carrier, your upper sideband, and your lower sideband frequency. Okay, so we have here another type of circuit. We call this the medium power transistor AM double sideband full carrier modulator. So this is also a collector modulator because as you can see, your modulating signal is still applied across your across the emitter of your of your circuit. Sorry, collector of your circuit. Okay? So, modulating signal applied at the collector, making it a collector modulator. Your VM or maximum is also equivalent to VCC. So, this has the same operation, okay, with the previous circuit, except for the appearance of a tank circuit here. Okay? So, the tank circuit is placed at the collector of your Q1. Since the transistor is operating between saturation and cutoff, collector current is not dependent on the on the base drive voltage here. So the previous example or the previous circuit, so the flow of your current IC depends on the zero point 0.7 or above or below zero point 0.7 of this carrier signal. However, with the tank circuit here, okay, so your collector current is not anymore dependent on the base drive voltage. Okay, so the voltage developed at the tank circuit is determined by the AC component of your IC and the impedance of the tank circuit at resonance. Okay, so the impedance of the tank circuit at resonance is dependent on the Q factor of your coil. So as you can see, the waveform for the modulating signal, the carrier, and your IC, okay, so the waveform for your modulating signal, your carrier, and your IC are just the same, just like on our previous circuit. Okay? And the output waveform here is symmetrical AM double sideband full carrier with an average of 0 volts. So what do we mean by with an average of 0 volts? So this is having a maximum value of plus 2 VCC and a negative value of negative 2 VCC. So therefore, having an average equivalent to 0 volts. Okay, so what is the operation for this circuit? So the positive half cycle of the output waveform is produced in the tank circuit by the flywheel effect. So what do we mean by the flywheel effect? So flywheel effect means that when Q1 is conducting, okay, your C1 is charging to VCC, okay, at plus VM. Okay, but VM is equivalent to VCC. So that will give us 2 times your VCC. So that is the time when your Q1 is on or when your Q1 is conducting. But when your Q1 is off, okay, C1 starts to discharge through L1. So in the opposite polarity or in the opposite manner. Okay, so when L1 discharges, okay, so your C1 charges to a minimum value, okay, which is equivalent to negative 2 VCC. Actually, the amplitude is the same, but since it is a reverse polarity, so it becomes negative 2 VCC. Okay, so that is what we mean by flywheel effect. When your Q1 is conducting, C1 is charging, and then when your Q1 is off, your C1 discharges through L1. So when your L1 is fully discharged, it will discharge through C1 in a reverse polarity. So therefore, we have your negative 2 VCC. Okay? So we have here the resonant frequency of the tank circuit is equal to the carrier frequency, and the bandwidth extends, okay, from FC minus FM to FC plus FM. So this will be the bandwidth of our AM or final waveform. So the modulating signal, the harmonics, and all the higher order cross products are removed from the waveform, leaving a symmetrical AM double sideband full carrier wave. Okay, so 100% modulation occurs when the peak amplitude of the modulating signal is equal to VCC. So this produces the positive half cycle of your AM envelope. Now, let us discuss, okay, the different circuit components in our previous circuit. Okay, so the different circuit components are R1. So R1 is the bias resistor for Q1. Okay, so your R1 and C2 forms a clumper circuit. So what do we mean by a clumper circuit? So this produces the reverse self-bias and in conjunction with the barrier potential of your transistor. So this determines the turn-on voltage for Q1. Okay, so it is the one which produces your zero point 0.7 pulses. Okay, so Q1 can be biased to turn on only during the most positive peaks of your carrier voltage. So those are the voltages above your zero point 0.7. Okay, so it is the one which produces a narrow IC or collector current waveform and enhances Class C efficiency. As you can see from our previous slides, okay, so your IC is in a form of pulses, and those pulses is how your output for a Class C amplifier looks like, okay? And the shorter the duration, the higher your efficiency. So therefore, Class C has high efficiency. Okay? So your C3 is bypass capacitor that looks like a short circuit to the modulating signal frequencies. So your C3 prevents the information signal from entering the DC power supply. Okay? So at RF, it is insignificant. So we have here your CBC. Okay, so this is your intercapacitance base to collector junction capacitance of our Q1. So at RF, it is insignificant because of the relatively so small value. But if it becomes significant, okay, so the collector signal may be returned to the base with sufficient amplitude to cause your Q1 to begin oscillating. So it can cause feedback. And when we have positive feedback, it will start oscillating, and we do not want that. Okay, so this is a modulator circuit and not an oscillator. So we don't want that. So we have to cancel whatever signal that it will be returning to the base. So how do we cancel that? So we must produce another signal that is equal in amplitude but it is oppositely directed. So that is the function of your CN. Okay, so CN is your neutralizing capacitor. So the neutralizing capacitor is used to provide a feedback path for a signal that is equal in amplitude and frequency but is 180 degrees out of phase of the signal that is being fed back through your CBC. Okay, so therefore, that is the main purpose of your CN in the circuit. So your CN there is called the neutralizing capacitor. So this is being used to eliminate whatever feedback that will come from your base to collector junction capacitance of your Q1, okay, or your CBC. So we have here your C4, like your C3. This is also a bypass capacitor, but it is an RF bypass capacitor. So your RF bypass capacitor has also a purpose of isolating the DC power supply from the radio frequency. Okay? So at the carrier frequency, C4 looks like a short circuit preventing carrier from leaking into the power supply or to the modulating signal circuitry and being distributed through that transmitter. So actually, these bypass capacitors have a function or purpose of what? separating the different signals, the different frequencies in your circuit. Okay? So we have here our next figure. Okay, so for our next figure, we have here a simultaneous base and collector modulation. So it says here to achieve symmetrical modulation, we must operate at maximum efficiency, develop high output power, and require um, as little modulating signal drive power as possible. We can make use of a base and collector modulations simultaneously. So from our previous examples or previous circuits, we say that collector modulators produce a more symmetrical envelope than low power emitter modulators. And we say that collector modulators are more efficient compared with our emitter modulators. However, your collector modulators require higher amplitude modulating signal, and they cannot achieve full saturation to cut-off voltage swing, thus preventing us to have a 100% modulation. Okay, so what do we do? What do we do is that we can still use of a collector modulator, but we can apply your modulating signal here simultaneously between the collector and the base. Okay? So looking here, look at here. So this is your modulating signal. It is being applied at the collectors. So it is applied at the collectors. And at the same time, your modulating signal is also applied at this Q1 here. Okay, so upon applying Q1 here, we have what we call collector modulation, because your modulating signal is applied at your Q1, at your collector, and your unmodulated carrier is being applied at your base. Okay, so the output of this one, which is being applied on this one, is already somewhat pre-modulated. So we have already done modulation here. So therefore, we have already a partially modulated waveform. Okay? So the operation is like this. Okay? So AM modulator uses combination of both base and collector modulation. So your modulating signal is simultaneously fed into the collectors of our push-pull modulators. So what is our push-pull modulator there? Your Q2 and your Q3. And to the collector of our driver amplifier, which is our Q1. So your collector modulator occurs in Q1 already. Thus, the carrier signal on the base of your Q2 and your Q3 has already been partially modulated, and the modulating signal power can already be reduced. Okay? So, modulators, they are not required to operate over their entire operating curve to achieve 100% modulation, because that the upon entering here. Okay, so upon entering here, they are already partially modulated. Okay, so those are the different types of discrete. Okay, so we call those discrete counterparts. Now, nowadays, we already have what we call linear integrated circuit AM modulators. So AM modulators are now in the form of an integrated circuit. Okay? So, this uses a unique arrangement of transistors and FETs to perform signal multiplication. Okay, so they precisely match current flow, amplifier voltage gain, and temperature variations. They offer excellent frequency stability, symmetrical modulation characteristics, circuit miniaturization, fewer components, temperature immunity, and simplicity of design and troubleshooting. Of course, when you are using integrated circuit, you don't need to troubleshoot anymore because we cannot really see what is inside that integrated circuit. Okay, so those are the advantages of your linear integrated circuit. Okay, so they can perform signal multiplication, which is a characteristic that is suited for generating AM waveforms. Okay, so IC, unlike their discrete counterparts. However, they have the following disadvantages, but as you can see, those disadvantages are very, very few compared to the many advantages of linear integrated circuit. Okay, so disadvantages includes low output power, okay, a relatively low usable frequency range, and susceptibility to fluctuations in the DC power supply. Okay, so we have here an example of a type of an amplitude IC integrated circuit. So it is called XR2006. It is a monolithic function generator, and this is suited for performing amplitude modulation. Okay, it has four different parts. Okay, so the block diagram inside, okay, the schematic diagram inside the specific IC composed of four parts. So the VCO, or the voltage controlled oscillator, you have analog multiplier and sign shaper, a unity gain buffer, and a set of current switches. Okay, so the VCO, frequency of oscillation, FC, is determined by the external timing capacitor C1 between pins 5, okay, so you can see between pins 5 and 6, and by the timing resistor R1 connected either pin 7 or 8 of your ground. Okay, so that capacitor C1 and resistor R1 will determine the frequency or the carrier frequency of your function generator. Okay, and the carrier frequency is given by the formula. Okay, so the carrier frequency is given by the formula FC is equal to 1 all over R1 multiplied by C1. Okay, so the frequency, where's my pen? So the frequency is being determined, the frequency of your carrier is being determined by the external component of your monolithic function generator. So it is not fixed. So as the user or as the designer, you can dictate what frequency of the carrier that you wanted, and the frequency of the carrier will be dependent on what value of your C1 and R1 that you're going to make use. And of course, our frequency is equivalent to 1 all over 2 pi R1 multiplied by C1. Okay, so that is because R1 and C1 is a time constant. So 1 all over time constant, so that will give you your frequency or carrier frequency. Okay? So we have here an example. Okay, so we have here an example. What will it look like when we connect it to different components? Okay, so this is a linear integrated circuit AM modulator using your XR2208 function generator circuit. Okay, so the carrier signal is the output of your VCO, and it is being dictated by the value of your R1 and your C1 at their specific pin configurations. So, and your P1 is your modulating signal. Okay, so this is your audio signal generator for your modulating signal. And of course, the output here your voltage output here is the output AM, amplitude modulation, based on your audio signal generator here, and your carrier signal that is dictated by your C1 here and your R1 here. So this is the linear integrated circuit AM modulator using your XR2206 function generator. So this function generator, the main purpose here is to have or to generate your carrier signal. Of course, you still have to apply your audio signal generator here. Always remember that an AM modulator, you have two signals, your modulating signal or your low frequency signal and your carrier signal. Okay, so this is an example of a very simple linear integrated circuit AM modulator. So if we have a low-level modulator and we have here a high-level modulator circuit, therefore we also have what we call AM low-level transmitters and AM high-level transmitters. Okay, so this is the block diagram for a low-level AM double sideband full carrier transmitter. So for low power, these low-level transmitters are used for low power, low capacity systems such as wireless, intercoms, remote control units, pagers, and short-range walkie-talkies. Okay, so we will be discussing each part. So the modulator part here, we have already discussed several types of modulator. The low-level type of modulator that we discussed was the emitter modulator circuit. Okay, and then the other parts of your block diagram here are somewhat already familiar to you. Okay, so let us discuss each part of your block diagram. Okay, so for a low-level transmitter, okay, used for voice or music transmission, the source of your modulating signal is generally an acoustical transducer. So when we say acoustical transducer, a transducer is a device, okay? A transducer is a device which changes one form of energy or type of energy into another. An acoustical transducer converts your sound signal, okay, or your sound energy to electrical energy or electrical signal. So usually, acoustical transducer includes microphones, okay, magnetic tapes, a CD player, or a phonograph recorder. Okay, so your preamplifier here is typically a sensitive Class A linear voltage amplifier with high input impedance. Okay, so the main purpose of your preamplifier here is to raise the amplitude of the source signal to a usable level while producing minimum nonlinear distortion and adding a little thermal noise as possible. Okay, so modulating signal driver. So your modulating signal driver is a linear amplifier that simply amplifies the information signal to an adequate level to sufficiently drive the modulator. So usually we can make use of more than one modulating signal driver. Okay, so from the carrier side, so we have an RF carrier oscillator. So usually we make use of crystal controlled oscillators. Why do we use crystal controlled oscillators? So one of the characteristic of a crystal controlled oscillator is that it is very stable and very accurate. Now, FCC or the Federal Communications Commission has a stringent requirements on transmitters' accuracy and stability so as not to interfere with their neighboring stations. So therefore, for RF carrier oscillator, usually the most common circuits used are those using your crystal controlled or crystals, okay, as their frequency determining devices. And then we have your buffer, okay, so we have your buffer amplifier. So your buffer amplifier is usually a low gain, high input impedance linear amplifier. Okay, so a buffer provides a relatively constant load to the oscillator, which helps to reduce the occurrence and magnitude of short-term frequency variations. So buffer amplifier, actually they don't really amplify. It is characterized as low gain. So it provides a relatively constant load to the oscillator. So what type of amplifier or configurations that doesn't really amplify or has a very low gain? So we usually make use of emitter, follower, or common collector configurations, or sometimes if we're going to make use of integrated circuits, operational amplifiers are usually used. Okay, so IC operational amplifiers. And then, of course, your modulator. So this is either an emitter or a collector modulator. And then we have intermediate and final power amplifiers, either linear class A or class B push-pull modulators. Okay, so, and then antenna coupling network. This matches the output impedance of the final power amplifier to the transmission lines and your antenna. Okay, so this is required with low-level transmitter to maintain symmetrical or symmetry in an AM envelope. So going back here, as you can see, your modulation class or your modulator or your modulation happens before the final element. So therefore, it is expected for low-level transmitters that after modulators, we can still find some amplifiers. So, modulation occurs before amplification. So, we need to amplify your output of the modulator circuits first before transmitting it, or before transmitting it to your specific medium. Okay, so therefore, because the output here is low power only because of the type of modulators that we're using, we still have to amplify it. And then we're going to look at the difference between these and the high-level transmitters. Okay, so let us go to high-level transmitter. So your modulator for high-level transmitters, so what is the difference? This is your block diagram for a high-level AM double-sided full carrier transmitter. So your modulator here basically does three things. Okay, your modulator here provides the circuit necessary for modulation to occur, of course, and at the same time it is the final power amplifier, and at the same time it is your frequency up converter. As you can see, after the modulation process here, okay, there is no more amplifier following that stage. So all of the amplification is now being done at the modulating circuit or at the modulator circuit. Okay, so no output amplifiers here as compared with low-level transmitters. So therefore, your power here is said to be high enough already, and it doesn't need further amplification prior to transmitter. Okay, so your modulating signal is processed in the same manner as in the low-level transmitter, except for the addition of power amplifiers prior to the modulating process. Okay, so we cannot see this. Okay, we cannot see this in your low-level transmitter. So the power amplifiers are after the modulation for low-level. It is during the modulation for high-level transmitters.
Okay, so this is because the carrier is at full power at the point in the transmitter where the modulation occurs and requires a high amplitude modulating signal to produce 100% modulator. Okay, so modulator is usually a drain plate or collector modulated class C amplifier. Okay, so that non-linearity will occur, and when there is non-linearity, you have your modulation. Okay, so we have here your class C efficiency because it makes use of class C amplifier, and we all know that class C has higher efficiencies of 80% and higher. Okay, so up converter is, it translates your low frequency intelligence signal to radio frequency signals that can be efficiently radiated from an antenna, and it can be propagated through your free space. So this is the main difference of your high level transmitters. Okay, so for high level transmitters, no more amplifications after your modulation procedure or process. Okay, so after modulator, it is already assumed that your signal is strong enough for transmission. They are already strong enough and it is ready to be transmitted. Okay, so we have here another term, trapezoidal patterns. Okay, so what do we mean by trapezoidal patterns? Okay, so this is used for observing modulation characteristics of AM transmitters. Okay, so usually coefficient modulation and modulation symmetry, it means the higher or the positive half is always the same as the negative half. Okay, so you have here the modulation characteristic. You can see the coefficient. We can solve for the modulation coefficient, and we can see the modulation symmetry using the trapezoidal patterns. Okay, so your modulation characteristics can be examined with an oscilloscope. So we can see this in an oscilloscope. So a trapezoidal pattern is more easily and accurately interpreted. Okay, so we have here several figures. So for letter A, so this shows a linear 50% AM modulation. Okay, so this is a 100%, this figure shows a 100% modulation. For C, this is more than 100% modulation. So that means your modulating signal's amplitude is greater than your carrier signal amplitude, or this is the trapezoidal pattern for an over-modulated AM. Okay, so it is considered as null. Okay, so in letter D, so this is how your trapezoidal patterns looks like if you have improper phase relationship. And finally, for letter E, this is a non-symmetrical AM envelope. So why non-symmetrical? Because our average voltage here is not equal to 0. That means your upper envelope is not equivalent to your lower envelope. So therefore, this is how a non-symmetrical AM envelope looks like. Okay? So another thing is your carrier shift. Okay, so carrier shift is often misunderstood or misinterpreted. So when you say carrier shift, the first thing that will come into your mind is it has something to do with the carrier frequency. Okay, but in reality, carrier shift has absolutely nothing to do with the frequency of the carrier. Okay, so carrier shift is sometimes called upward or downward modulation. Okay, so this is a form of amplitude distortion introduced when the positive and negative alternations in an AM modulated signals are not equal. This is an indication of the average voltage of an AM modulated signal. Okay, so you can see based on the carrier shift whether you have a symmetrical or a non-symmetrical modulation. Okay, so when the positive it is said to be positive when the positive alternation has a larger amplitude, or it can be negative when the negative alternation has a larger amplitude. So for figure A, this is what we call a linear modulation, wherein our average voltage is equal to 0. So the positive alternation is just equivalent to the negative alternation. So for letter B here, it is said to be a positive carrier shift. Why? Because your positive alternation is greater than your negative alternation. And if we get the voltage average for this, we will be having an average equivalent to a positive value. Here, our average here is always equal to 0 for symmetrical. Okay, and finally for letter C, this is a negative carrier shift. Why? Because the negative alternation amplitude is greater than the positive alternation amplitude. And if we get the average voltage here, we can have an average voltage that is equivalent to a negative value. Okay, so lastly, we have an AM envelope. Okay, so these are the types of AM envelopes produced by complex non-sinusoidal signals. Okay, so it says here that non-sinusoidal signals are considered as complex forms which are comprised of two or more frequencies. Complex repetitive waveforms are complex waves made up of two or more harmonically related sine waves. Okay, so they are either in a square, rectangular, or triangular waveform. Okay, so complex modulating signals can also contain two or more unrelated frequencies. For example, voice signals that are originating from different sources. Okay, so it says here that the shape of the envelope resembles the shape of the original modulating waveform. Okay, so in the first figure or in letter A, we can see that when you have a triangular modulating waveform, the shape of your envelope is also triangular. Although you can see that the carrier is still in the form of a sinusoidal waveform. Okay, so the type of modulating signals that you're going to make use will dictate the shape of your envelope. So if you have a square wave, okay, so the envelope will look like a square wave, but the carrier signal is also in a form of a sinusoidal waveform. And our third is voice modulation. Of course, voice modulations or voice is made up of several frequencies. Okay, so this is how your envelope will looks like if you have an AM envelope for voice modulation. Okay, so that's it for our video. Thank you for watching, and please don't forget to hit the like button after watching. Okay, so thank you very much and God bless.